Imagine for a second that you are inside a balloon. You are a gas particle that's whizzing about inside this, what seems like a spherical shell of a balloon. It's red, and you see the glow of red inside as you look around. There are other atoms also whizzing about, and maybe atoms doesn't complete the picture. What you are actually is a molecule. So let's take, for example, oxygen gas molecule. So you don't stand alone. You have a twin. You are oxygen, and you've got another twin, another oxygen atom, and you guys are joined together with your hands, and you're whizzing about looking at other oxygen twin pairs, other slightly different nitrogen twins, maybe even a couple of loose carbons that have somehow found their way amongst oxygen twins to make carbon dioxide. You guys are just whizzing about within the balloon. Suddenly, you see an influx of other oxygen twins that you haven't seen before. They're coming from the very bottom of the balloon. They're entering the balloon. And suddenly, everything feels a little warmer. You feel a little anxious, and you whiz about just that little faster. And more come in. And more. The anxiety almost takes over you. And you start going crazy. You drag your twin with you, your twin's dragging you as well, and you guys start hitting the outside of the balloon. The more you hit, you find the more others are hitting as well. And the more actually the space grows. Suddenly the balloon's gotten bigger and it keeps getting bigger. And we have some more space that you didn't have before. And you chill a little bit. You go, okay, maybe this was an illusion. We're fine now. What we just imagined is what happens when you increase the pressure inside something. Now, this isn't anything profound, right? You add more air, you increase the pressure inside something, be it, you know what, forget gas, be it in light. The more you're pressured, more often than not, the more the volume expands. So you usually have a lot to do and the volume of your work grows. Or in the case of physics and gases and thermodynamics, the more the space grows because pressure pushes and forces the space to grow. But again, this is a very, very specific example with something that can grow. Sometimes spaces are fixed. There's rigidity. Like, let's say a metal cube. No matter how much air you pack in that, because it's metal, it might bend. No matter how much pressure you add there, it might bend, but eventually it's going to explode. It's not capable of just being flexible and growing to handle pressure. In the same way, imagine a syringe. You fill it with water, close the other end, hold it with your finger, and you push the syringe. The water is trapped, but you're somehow pushing on the syringe still to try and get it to move. And you find that after a certain point, you just can't move the syringe because the water there inside, the space, the pressure that's built up with the water within the syringe is incapable of expanding the space with it. So it doesn't move. And anyway, that is an explanation or an example, an illustration of what is otherwise known as ideal gas law. Now, this ideal gas law applies very, very specifically to the balloon example, not so much to syringe. There's different maths that governs that, but ideal gas law essentially says that the product of pressure and volume is equivalent to the internal energy, i.e. the temperature that's inside the balloon. So if you again think, before you expanded the balloon, when you were in there and there was more particles coming in, more of the twins, oxygen twins, you felt hot. You felt this feeling of, oh, I want to get out of here. So imagine TV equals nRT as an equation. T has gone up, V hasn't. So your T temperature has also gone up. Now, given the nature of the balloon, it allows V, the volume, to change also. So when pressure goes up, volume might increase to compensate for it, in which case pressure drops again, and you end up getting a very constant temperature. But again, the number of particles has gone up. So when you have your ideal gas law equation, which again says PV equals nRT, N has gone up. So something on the PV side must go up, and that can be pressure or that can be volume. Now, that's just the ideal gas law. For any of this to happen, we need energy. Because how do particles just randomly find themselves inside a balloon, right? You need some source. You need somebody going, hey, I'm going to expend some energy to do this or that. And that's where the concept of heat transfer becomes really important in physics and thermodynamics, in anything in life really. To do work, go with the flow requires energy. There are different ways this energy can be transferred, and more often than not, in thermodynamics or thermal physics, we can actually put every process, most processes, in 4 buckets. Like we can class them and divvy them up so we can analyze them separately. The easiest one, I'll say, is a isovolumetric process. Or there's another term for this, an isochoric process. This is a process where the volume just doesn't change. So you're looking at not a balloon, but that steel tube that I mentioned before, or a syringe that's fixed, a piston that's fixed, just stuff that doesn't change, doesn't have the flexibility to change its volume, in which case your V is fixed. If you go back to your ideal gas law, PV equals nRT, and when V is fixed, when you change the pressure, add more molecules or whatever, temperature changes. And that is representative of the work that you're doing. Now, the work that you would be doing in an isovolumetric case is actually 0 because nothing changes, right? Like the system is incapable of change. This process doesn't produce change in the physical sense, but it does produce a change in temperature or pressure or things that are less tangible, that we need sensors of some kind to measure indirectly. Another type of process, so that's the first bucket. We still have 3 more to explore. A second bucket is an isobaric bucket. So this one's a weird one. All it is it's a process similar to isovolumetric, but the pressure doesn't change. And in such a situation, there is work. You can see things, you can see the balloon expanding, but the internal pressure stays the same. Now, an easy place to get confused is, how does the change even happen? Like, how does volume even change? You need some change in pressure. You need pressure to change and build up, the volume to change. And you would be absolutely correct when you say this. When we talk about processes and we analyze them, we try to class them in these buckets. We look at the starting point and the end point. So if at a starting point there's some number of pressure, we can measure it in atmospheric units. So 1 atmospheric unit's worth of pressure. In which case, that's where your starting point. You add more molecules in that space, and the pressure increases. But because you're in a balloon, the space expands and your pressure drops back down to 1. In that case, if we just look at the starting point versus the end point, pressure hasn't changed. This makes that balloon situation an isobaric process. So that's 2 of 4. Isochoric is the first process. Isobaric is the second process. The third process is a very interesting one. I'm sure you can guess maybe at this point, because each process relates to the ideal gas law, which says PV equals nRT. The last one is second last one is an isothermal process. And similar to isochoric and isobaric, this is a process where the temperature doesn't change of a process, of a system. So you can think of maybe a good example is a heat engine, or even a process of a balloon expanding and contracting. It's almost a cyclic process. So you heat something up and it expands, and then you cool it down and it contracts back down. Isothermal processes are very, very interesting because, again, the goal there is the temperature of the thing doesn't change. A very similar, interesting process is the melting of ice. So what happens is when ice melts, its temperature actually doesn't change. What does change is the pressure of that little bit of ice, internal pressure, and volume, like the volume that this bit of H2, that type of H2O molecules take up. It's a very interesting space to look at, and we'll talk more about what fusion and latent heat of fusion means and what changing of states means. But before that, let's explore the very last process. This is an adiabatic process. An adiabatic process is one where there is no heat transfer. So that just means you can't heat things up. So if you think about an ice block again, our previous example, you have to melt the ice. You have to put in some energy to melt the ice into water. And yes, its internal temperature hasn't changed, but you still were adding some sort of energy to release the ice molecules from within themselves and make them into water. So that would not be an adiabatic process. To imagine an adiabatic process, imagine quick processes where there's no time for the molecules or things inside anything to interact with the rest of the world. So that would be pumping a balloon really quickly, right? That is, you're not giving time for these molecules to interact with the world or do anything really. So what ends up happening is there's zero heat transfer between the molecules and the environment. So those are the 4 buckets of processes that we can classify anything into. And when we are able to classify anything into this stuff, we can start analyzing them. So I want to actually dig into the second to last bucket, which is the bucket of isothermal processes, especially the process of turning ice to water. You might have seen the fact that ice is actually less dense, or you might have heard of this, less dense than water. So what happens is when water freezes, ice, or is starting to freeze, ice tends to float back up to the top. It takes up more volume than what water would take up. Very, very interesting fact. But excuse the yawning, given it is Snoozics, I think it's fair that I myself feel sleepy. And very interestingly, this property of water is what actually has led to us as humanity surviving the astronomical event that otherwise killed and wiped out a whole species of dinosaurs, just all dinosaurs. Because what happened is when ash filled the sky, either through a meteor or through a volcanic eruption, whatever the source, ash and ashy clouds filled the globe. It literally covered the globe. Imagine being inside a balloon. That is literally exactly what people were inside of, except this balloon was suffocating you. What actually happened was, on top of suffocating you, it started stealing your warmth. So imagine being suffocated and frozen to death. Very gruesome. But this is where science magic happens. Because as this is happening to water on oceans, water starts to freeze, floats back up to the top because it is less dense, and almost forms a very protective shield around the ocean, on top of the ocean. So all of the molecules and life that was under that bit of ice, underwater, in the ocean, continued on. No joke, the heat that was there in the water was trapped and protected and kept in by ice, very ironically. And to me, that's what's so wonderful about science and the world and everything as we know it. Because what we thought would freeze us kept us warm, which is so interesting. And as the ashy clouds started disappearing, we went back to normal. Ice started melting away, and fishes and creatures from underwater were finally able to swim back up and evolve. And now you are here listening to me, and I am here talking to you. Very, very, very interesting stuff. The reason I talk about this is I want to just highlight how special ice and water are. Another way they're special, as actually all liquids are, is when you have ice and you try and heat it up, it does become warmer. But after a certain point, it stops changing temperature. And no matter how much heat you put towards it, it doesn't change temperature. Instead, what happens is it starts changing phase into water. That's why melting is so special. And the reverse is equally as true. When you have a bit of water and you're freezing it, its temperature drops past a certain point. But then after a certain level, it doesn't drop. Instead, the heat that it loses goes towards changing phase, makes it change phase from water to ice. And you might actually notice that with your water bottles. When you put your water bottle in the fridge and keep it very still and you don't touch it, temperature would have dropped just to the point of the temperature of ice. But its temperature wouldn't change past that. So it's in this weird phase of water-ice phase, with its temperature being at the threshold temperature for ice. When you touch it, you almost kickstart a reaction that fully changes the water's phase into ice. I highly recommend you try and see how that happens in your fridge. All that you need is a little water bottle and some water. But for now, of course, stay in bed. Very, very interesting phenomenon with changing phases. It's also true on the other side of boiling, because we've just talked about melting and freezing. This is also true between gas and water. You can absolutely heat up water and it will reach a certain temperature, and after that temperature it stops changing temperature and instead starts changing phases into gas. That's the whole point of boiling. That's why you see bubbles when you boil water, because what's happening is any extra heat that you add, you brought all of these water molecules to a certain temperature, and any extra heat you add is actually forcing them away from each other and into a different state, a gaseous state. Very, very interesting stuff. On this topic of on this topic of pressure and volume, I want to actually make an honorable mention to Cepheid variables. So Cepheid variables are very, very cool. They are a very interesting type of star, and it was It's a type of star that basically expands out because its internal pressure is just so much that gravity almost loses for a second. Gravity cannot hold the star together. And so the star grows and it expands really brightly. But then after a certain point, the pressure can't keep gravity off and gravity starts winning again. And so the star starts imploding, collapsing in on itself, and it dims and it becomes much smaller and denser. But then in the act of becoming denser and smaller and pushing against itself, pressure starts building up. Photons and light starts building up inside the star. And you have another slow expansion of the star, releasing light to trap the light. And then, pressure drops, but then gravity wins again. It contracts, pressure builds, light builds, expand, release. That cycle that happens on a predictably variable rate is called, and it doesn't happen in all stars. It only happens in a select number of stars at a very select mass. And these are called Cepheid variables. The process that we've just talked about is the same as what ideal gas law does, where, hey, if you decrease volume, pressure is going to go up, temperature is going to change like this is what happens. And it's almost the same thing. And these Cepheid variables are so interesting because they are what we use to measure distances in intergalactic regions of space. They are what we use to map out the space and the world beyond our own. They are what we use to go, oh my God, Andromeda is actually its own galaxy and it's this many light years away. Shout out Edwin Hubble. Well done. And this technique of using Cepheid variable, also shout out, was discovered by Henrietta Leavitt. I'm so sure I'm pronouncing that wrong, but Leavitt's law revolutionized astronomy and how we picture the universe. Really, really interesting stuff. And it goes to show that physics is all interwoven. You can't isolate thermodynamics and just study it in silos, looking at balloons and stuff, because that thermodynamic physics is applicable everywhere there are gases, everywhere there are particles interacting with each other, everywhere there is energy. In saying that, the amount, I want to sort of go back to our water and ice example, because I mentioned that the more heat you add, the more the temperature changes, but then after a certain point, no matter how much heat you add, the temperature doesn't change because all that energy is used up by, let's say, ice to change state into water. There is a term here that I should introduce. It's called the heat capacity. And heat capacity of, let's say, water or any specific material essentially defines how much energy you need for that material's temperature to change by a singular degree. And so you can think of the units look something like this: joules per kilogram so that's per kilograms and per unit of mass. So joules per kilogram per temperature, per Kelvin. So joules per kilogram per Kelvin. And it's, again, very interesting. There's a very interesting story and history with heat capacities, because actually this concept of heat capacity and the amount of energy you need to change the temperature of something isn't exclusive to gases or liquids. It is also applicable to metals, because metals are another thing that heat up and cool down in our everyday life. And I want to talk about this very interesting story for the next couple minutes or so, maybe more. So what we found way back in like the 19th century, 1800s, was actually this really interesting relationship amongst all metals. We saw that the heat capacity for most metals was actually a constant. It was the same. It was the same constant 3 times R, where R is some Boltzmann constant. Initially found by Dulong-Petit. It's called the Dulong-Petit law. And it basically says that the specific heat capacity of a solid element is equal to 3R, where R is the gas constant, as I mentioned. Nobody could explain why this was the case. Literally nobody. Until Boltzmann came along and he's like, actually, this kind of makes sense. If you think about just how heat is distributed across things, for something to be stimulated and vibrated, there are 3 different ways it can vibrate. One is up and down. So that's up and down. The other is side to side. The other is in and out. So just think about 3D space and the different ways you can move through it. There are three ways. And so that's where the 3 comes from, is what he says. And so with gases, there's 3 ways of vibrating. Sorry, with metals, there's 3 ways of vibrating things. So context, metals form into the structure that looks like a lattice. Lattice is like a uniform patterned way of structuring things. And atoms happen to arrange themselves in a lattice in a metal. So it makes sense that you've got to when you put heat into a metal, you just vibrate it in 3 different ways, which is what increases its internal energy, which increases its temperature. Now, that was kind of an okay explanation, but it was still incomplete, because what we actually saw was at really low temperatures, actually heat capacity was nearly 0, as in it was really easy to excite metals and change their temperature when they were initially at a lower temperature. And then when they went to a higher temperature, you would need more energy to take them to an even higher temperature. And then after a certain threshold temperature, that it became a constant, like the heat capacity was a constant. This picture, nobody really understood until, of course, our boy, our icon, we know him, we love him, Einstein came along and he was like, bestie, chill. It's all about vibrations. Still, he said, actually, there is this concept called resonance. You cannot just throw any bit of energy at your metal. This metal needs to be excited with at least this much minimum amount of energy. So let's take diamond, for example. It has nearly 0 heat capacity at really low temperatures. And so he basically said atoms vibrate with a characteristic frequency, and you need that amount of energy given by E equals hv. And he said that at low temperatures, that resonant frequency is like statistically harder to reach. But then that still sort of didn't explain, like it was an oversimplified theory, didn't necessarily explain what was actually happening. So that's when Debye, our good boy Debye, came along, and he said, actually, you are assuming all atoms in the whole lattice have the same characteristic frequency. This is not the case. They can vibrate in whatever ways, many, many ways. And one of the ways is they can vibrate in phase, like you can excite them in phase. So that is literally what gives rise to sound waves, right? So if I punch something and that punch travels in phase perfectly through the solid into the other side, I will hear that sound come out. And it's actually one of the biggest reasons why sound travels faster and like louder in solid. So if you put your ear to the wall, you will hear sound. Another reason why you can't hear anything in space, it's because there's no solid to carry the wave. So these are what we call acoustic phonons. And unlike acoustic phonons, you can have situations where atoms move against each other, so not in phase. like not uniform, not nicely orchestrated like a Mexican way, but just very randomly. And when that random movement happens, they brush against each other. You get dipole-dipole interactions, basically electromagnetic interactions, which give rise to light and optical stuff. And that is called the optical, those are called optical phonons. And it's, we can excite them using light, and we can observe them and see how things interact and how stuff happens. Very, very interesting fields of physics. It's, we can use these phonons to understand the band structure and metallic properties of metals because they behave this way. It is so interesting. This explanation, tying together quantum and tying together the superposition principles of different things can be in different characteristic frequencies, and they all sum together nicely or not nicely. And I hope this has put you to bed. To end things off on a better note, this has been Snoozics, a series of videos that I'm doing just to help everybody sleep, to help myself sleep. Idea came from when I was talking to my mom about speed variables, and she literally just fell asleep listening to me. So I'm hoping to kill two birds with one stone. I get to yap about physics and scratch that itch that I always have. You get to hopefully fall asleep in a nice way and learn a little bit about physics on your way. This has been Snoozics, as mentioned, episode 1. I will see you next episode.